We'll start off today with, we're not actually going to start here. We'll start here when we start, but we'll talk about what's the order of things now. First, let me talk about office hours this week. Now, ever since I picked up the second meeting term course that I'm here until 8 o'clock at night on Tuesdays and Thursdays, give me 12-hour and 15-minute days on Tuesdays and Thursdays. So my Mondays and Wednesdays have gotten scrunched up some. But most Mondays and Wednesdays, technically I'm supposed to leave at 2. Just about every Monday and Wednesday I've got so much to do, I'm here later than that. Usually at least 4:45 or 5:15, somewhere around in there. However, tomorrow, Wednesday, I'm going to have to be leaving between 2 and 2:30 because I've got a meeting on the Birmingham campus at 3 o'clock. So I won't be in my office, even though I'm not supposed to be there. I won't be there for sure until I get out of class at 1:55, and I'll probably have no more than 15-20 minutes in my office before I'm heading to Birmingham campus. And then I'll leave from there to go home, so I won't be coming back here. Technically, I'm not supposed to be here at all, but most of the time I am. But on Friday, I'm supposed to be on the Birmingham campus from 7:45 to 11:45. This Friday and next Friday, I won't be there at all. I'm having a new round of treatments starting this Friday. They're giving me a reduced dose because it's the first time I've had it. And they're going to spread 300 milligrams, which is not very much, over 7 hours. So they're taking it really slow. And if everything goes well there, then the next Friday, they'll give me a full 1,000 milligrams, which is still not very much. Again, probably stretch it over 7 hours. So both days I'll be there at 7:30, so I won't be on campus at all. After that, it's every 2 months, so I won't miss any more Fridays because of that anyway. Knock on wood. Okay, so anyway, that's that. Now, what I was thinking of doing today, and this was based on our lab last time, we did not get to finish the lab, okay, completely. Got to get a copy of the lab here. There it is. Okay. Okay. We are recording, so this is all up here. I think that most of the teams that were there, okay, finished collecting data. Is that right? And on the last part, exchanging data, right? Whether you finished calculating, I don't know. But the lab was put together. Did everyone bring his lab today? I gave you one. Okay, good. Everybody got a copy? You don't. Oh, yeah, you weren't here before. Okay. So you can maybe get the data from some of your classmates or somebody. Another copy here. And again, I'll say this again. I said it earlier. This is the longest lab that we're going to have all term. Sorry to hit you this was the beginning. And the most involved lab that we have all term. But what we did, for those who weren't here, and for those that were, we started on the front page, read that stuff. We started doing part A, and we did pretty much that, kind of pretty much like it said, nothing too new there. And the part B, area, oh, and by the way, the data, the instructions are on page 15 for part A, but the data goes on page 23, circles and ratios, near the top of the page. That's where the data goes, okay? And there's, after you measure the data, then you do the ratios, and after the ratios, the manual's here. There you are. Now, I saw a couple of emails from you, but I didn't get a chance to read them. Okay. What's that? I can't hear you.
He understood it.
Oh, okay, sorry. My hearing is so bad. Okay, so your data go there. So if you, hopefully you got them all in. But once you collected the data, that's on the first 2 lines there. Then you do a ratio. Most of you went on and calculated those. Then you do an average of the ratio. Most of you did that. And then the experimental error, we talked about that. It's recorded in Screencast-O-Matic, so you should be able to follow that too. So you can get data from others who were there and fill in, do your own calculations. Okay, then the second part, the part B, that's at the top of page 16. Okay, follow the instructions. Now the one exception for this is we didn't have cubes, we had rectangular blocks. Okay, and you can see how to do it. The rest of it you just do as we did. Fill in the data on the bottom of page 23, and once you do the ratio of area to volume, then you answer the question back here on page 16. Number 6, describe a pattern to generalization. So anywhere you see a big blank like this, you need to fill something in. You need to answer. I mean, it probably can do it in a sentence or two, okay? But just fill in something there to answer those. It actually is 2 questions, so maybe 2 sentences to answer those. Then the last part we did was mass and volume, and it gives all the things to do there. We pretty much did that as it's listed. We didn't have boxes like this. We had boxes, but you can get the data from your classmates if you weren't here. And the data, again, on that one goes on the very last page, or not the last page, page 24. And that's where it is. Now, each team did one size of container, and then once you got the size of container, share that data with the other 2 teams, and you get theirs, they get yours. Okay? So that's how we finish that. But then, when you've done that, putting the data on page 24, you go back to page 18 and answer those 4 questions there that have white space after them. So don't forget to do that. Okay? Now, I'm guessing that most of you got most of that done in the lab. I don't know if you went back and answered questions. You had 1 on page 16 and 4 on page 18. Okay? Everybody pretty much get that done? Okay. Now, if you did or didn't, you got some time today to work on it. Now, my question for you on page 19. On page 19, it says results. Now, this is what questions you answer based on what you did. Okay? Did y'all get that done? I don't think we had time in class. So that's what I'm going to give you time for today. If you haven't got the earlier data done, get that. If you have got it done, which I think most of you have, then start working on the questions, results on page 19. And that goes over to 2 questions on page 20. And then there's some problems. It's just really one kind of big problem, but it's broken into several questions. That's the bottom half of page 20 and page 21. So you do that as well. Okay? And by the way, I forgot to say this. On the part C, those questions you were answering and the things you were following, on page 18, that's the top of the page, make a graph. And I think y'all worked on the graph last time, didn't you? And probably got the graph done. That goes on the very last page. It's an unnumbered page, but the graph goes there. I think most of you who were there got that done. If you weren't there and didn't get it done, then get with somebody who was there and work on that. Okay, so basically, I think you have a few questions to answer. You have the 1.5 pages of result and 1.5 pages of problems. What you figure? Half hour? Or a little longer?
3 or 4.
Say again?
3 or 4.
3 or 4 half hours? Okay. So get working on that, and if you have questions, I'm up here, or see your classmates, okay, if you got something there. Okay, everybody got a lab, and you can work on, are there any questions about what we're doing? We didn't have time to finish all this. Now, most labs we will finish in the 2 hours. This one, we were running just a little short. So, if you want to get with your lab mates, you can do that. But try to wrap those labs up. Now, the lab isn't due, let me say this, the lab technically isn't due until a week from today. However, remember the test on Chapter 1 is at the last 30 minutes of the day, 7:15 to 7:45. But if you, I think if you have done the lab, you'll, at least a few of those questions on the test, this will be helpful to you if you've done this before you take the test. So that's why I'm giving you time today and not just say, take it home and do it. Do it now so you can do better on the test when it comes up at the end of the day. Okay? Any questions? Okay, now let's not waste time. Let's take best advantage of the time and let's get done as soon as you can. Because we really need to get on to Chapter 2. We started it last time but didn't get very far at all. And remember, you don't have to finish all the lab today, but let's just figure, okay, that's why I was asking. Half hour, hour, what you want to set aside for it? How about this? When I see most people, or at least some people finishing, we'll go in and curtail it then. You can do the rest of it. Well, you got a week to work on it, okay? That's okay? All right. What's that? Okay, good deal, thanks. Several people have turned in the things on their syllabi, so I appreciate that. So about 10 too. All right, I'm going to pause screencast-o-matic. Formula for calculating the volume is length times width times height. Okay? What you need? Okay. Now, since we have had a new person come into the room, into the class that wasn't here before, let me go over just a couple of things. We started in Chapter 1. And have finished it, and you were working on the lab for Chapter 1. Now, the last 30 minutes of the day, that's 7:15 to 7:45, we're going to have the test on Chapter 1. Since you weren't here, if you don't feel ready for it,
I'll be okay.
huh?
I'll be okay.
Okay. Well, I was going to say you can just leave at 7:15 and then come back sometime and make it up. Okay.
Thank you.
All right. As I said, the first lab is the longest lab, the most involved lab. It's taken the most time. Other labs will be much shorter. The second lab we'll do, which we won't have time today, but when we do it, it's going to be, you'll find much shorter, okay? There will be several labs on the later chapters. In fact, most of them have 2 or 3 labs each, except for the last chapter only has 1. So, this chapter, the first chapter was a short chapter, 1 lab. This chapter we're on now will have probably 3 labs, and next chapter probably 3, the next one 2 or 3, next one 2 or 3. Okay, so and then the last chapter will just have 1. So we'll build up labs faster when we have tests. But the other thing, now I've already put out, and this is for all of you now, in Blackboard. Okay. Are y'all all familiar how to get the Blackboard and do it for this course? Okay, when you get there, in the upper left column, at least in the instructor side, I think it's pretty similar in the student side, there's a series of tabs there, okay? Like the second or third one, somewhere in there is one that says Content. If you go to the Content tab, you'll see the syllabus, and several people have already turned in the last page of the syllabus, meaning you've read it, understand it, and that kind of stuff. Now, I'll get to the second part later. Then there's also in the content is the research paper instructions. There is a research paper due required in the class, so start working on that. No one's given me a paper, well, maybe one person's given me a paper topic so far. So be thinking about that. Get started. You only have 8 weeks, okay? This is a mini term, okay? Then the next thing in there is my locator card. Maybe one or two little things by a work study student did it, and I didn't check it carefully, and I saw a couple things later I probably will have to change, but it's really minor. Then the next thing in there after that, I believe, is the YouTube videos. So if you want to see or hear what happened in the first class, we went over syllabus, research paper, locator card, safety, okay, and we got started in chapter 1. And then the last class, we finished chapter 1, and we did the lab. Now the lab, not everything will be in there, because obviously taking measurements, you can't do that for everybody in the labs, but you can at least hear what was going on in the lab. And then today's is going to be recorded too, and it'll be loaded under YouTube video. And there is a playlist, and that playlist will contain all the classes in this course. And again, I'll say to you, because this ends so late, I have to shut down the computer. It doesn't keep uploading it then. So it's the next day I come in, turn it on, and it starts uploading it. But then I have to have a break. Like tomorrow, I won't have a break until probably late afternoon that I can move it from YouTube to the playlist. So don't look for it immediately. Most of my classes, I have it there a little bit sooner, but this one, because we end so late, and I have classes early the next morning, and I usually don't have office hours until much later in the day, I won't get it moved over then. And in fact, sometimes on Thursday night, okay, let's take this Friday when I have a treatment. If I can't get logged in, and sometimes at UAB, the Kirkland Clinic, you can easily get logged in. Other times it's really hard, and sometimes it dies on you and stuff. If I can't get it to work there, then it'll probably be later in the weekend or maybe even Monday before I get Thursday's class loaded. I'll try to have it done sooner, okay? And then the final thing, and this wasn't there when we went over it before, I finally got all the PowerPoints up in Blackboard, okay, under content, okay? So everything pretty much is under content now. Any questions? All right. This is chapter 2 material where we left off last time. If you got your books, this is along about page 26, first page. Now, different people have different editions, so you'll have to find that page. It's under describing motion. And this is talking about explaining motion. Now, this is all in the overview. We'll come back and do this in more depth later. But the basic ideas of explaining motion are 3 of them that we'll be talking about. First, we'll talk about forces. Now, we're not there yet. We got to do the describing motion first, then we'll get to forces. Then we'll do inertia and mass. Those are related to each other. And then we'll do Newton's 3 laws. Now, Newton's had lots of laws, but we'll do his 3 laws of motion. Then we'll do applications of motion, of these, and that will involve momentum and impulse, a little bit on circular motion, Newton's law of gravitation. Boy, you're seeing his name all over the place, aren't you? And then we'll look at another application, which is the Earth satellites. And we'll be looking specifically at the geosynchronous satellites. What does that mean? Any ideas? Those that stay in the same place all the time. I mean, they're moving because the Earth's spinning, but they stay over the same point all the time. Where do you use those? Have you ever used one? Any of you got GPS? All right, those are geosynchronous satellites. They're sending those signals. How else does it know where you are, okay? And where you're going, and all that kind of stuff. Okay, you got that. Any of you have a disk? As in disk TV, digital, direct TV, any of those? You know, they're pointing one direction. That's because they're pointing right at that satellite, and that's a geosynchronous orbit. So we'll do a little bit about that. We'll do some other things on satellites too, but we'll mention those. All right, this is again overview of what we're going to do in the chapter. Let's go back then to starting about describing motion. First thing we're going to talk about is measuring motion. And by the way, if you're following in your book, this is topic 2.2, page 27 or thereabouts, depending on which edition you have. Okay? Measuring motion. Okay? Two fundamental components of measuring motion. What do you reckon they are? If something's moving, it's, you got a displacement. That's usually a distance, okay? Displacement or distance. What's the second thing? Time, okay? So the two fundamental components, a change in position, and that change in position doesn't happen immediately. It takes some finite amount of time, so you also have a change of time. So these are the two fundamental components in moving. Something's moving, it's changing its position, and it's taking some time to do so. Right? Now, what can we get out of that? Change of position per change of time. Well, here's an illustration first. Here's a car going down a flat, level highway. Okay? At time t equals 0, when you start the stopwatch, okay, the car moves 1 mile in 1 minute. Okay? 1 minute on the clock, 1 mile of displacement. Second minute, it moves another mile, 2 miles now. Third minute, it moves another mile, 3 miles. Fourth minute, it moves another mile up to 4 miles down the road. What can you tell me about that? Say again?
How fast?
Okay, how do you get how fast? Say again?
Time and distance.
I can't hear you.
Time and distance.
And how do you get it? Those are up here. How do you get how fast?
The amount of distance.
Yes?
By time.
Say what by time?
Distance by time.
Divided by time. Exactly. You divide the distance by time. So what's this car traveling at?
60 miles an hour.
Exactly. Okay. It's 1 mile a minute, but there's 60 minutes in an hour, so that's going 60 miles per hour. Absolutely. Okay. Before we even got there, y'all know how to do it. Okay? There's 3 important combinations of these lengths and time. You've just hit one of them. And what was that?
Distance by time.
Which is called? Speed, exactly. Okay? Speed is distance divided by time. Now that's distance divided by time. Now a change of position could be measured in a different way. Not just how far you moved, but how far in what direction you moved. For instance, this morning when I drove to work, we'll just round it off a little bit, I drove probably 18 miles, just guessing. That would be the distance. But if I was going to be a little more precise, I would say I drove 18 miles to the southwest. Because I came from Birmingham heading toward Bessemer. Okay? When I added direction to it, what have I just described? No, not yet. We're going to get there. But just to my distance, I added direction. Distance in a direction, that's called a displacement. That involves what kind of quantity? We talked about it before, or did we? No, maybe we didn't. Teaching so many different classes. I guess it was one of my math classes we were talking about it. A displacement is a distance in a direction. A distance is just a distance. The difference there is one has a direction and one just is a quantity. The one with just a quantity is called a scalar quantity. Time, for instance, is a scalar quantity. Distance is a scalar quantity. But displacement, when you have a direction with it, that becomes what kind of quantity? Anyone know? A vector quantity. A vector has a magnitude and a direction. So the second of these, in everyday English, we think of speed and velocity about the same thing, don't we?
No.
Why not?
Speed is how fast you go, velocity changes with direction.
Yes, exactly. Velocity is, but in everyday English, they mean about the same. Most people don't talk about velocities as being vectors. But in physics, in physical science, speed is a scalar quantity, velocity is a vector quantity. Isn't that convenient? Speed scalar, velocity vector. Same letters. Okay. Because velocity is displacement over time, meaning the vector distance with direction divided by the time. Okay? Whereas speed is just distance divided by time. All right. Now, one more. What's something else we can do, especially with the velocity and time? What do we do to get from to speed or velocity? We took position and, what do we do? What's the relationship? Divided by it. Okay, what happens if we take velocity and relate to time the same way? Divided by time, what does that give us?
Speed.
Say again?
Speed.
No? Speed or velocity divided by time gives us something else. Okay. Now, I bet you, most of you, because I know a lot of you are automotive, I bet you talk in terms of this lots. When you say, man, this can go 0 to 60 in so many seconds. What are you talking about there? 0 to 60 is a change of velocity, right? From rest to 60 miles an hour, right? Is that what you mean by 0 to 60? In a certain time, what are you talking about then? Acceleration, you got it. That's your acceleration. Acceleration, not X. Acceleration. And now, here's sort of the physics or physical science way of talking about it. Speed is the time rate of change in distance. Velocity is the time rate of change of displacement. And acceleration is the time rate of change of velocity. Every one of these is a time rate of change. Get used to it. Because just about everything we do in this course and in physics, once we get a quantity and we're playing with it and use it and say, hey, that's pretty good stuff, well, let's see what happens when we take a time rate of change of that. In other words, divide by time. We will do that over and over in the course of the over the time that we're in here. Just about every field of physics will do this type of thing. Well, we've got this. Now let's take the time rate of change. What happens if we divide by time? Divide distance by time, you get speed. Divide displacement by time, that's a vector quantity, you get velocity. Divide velocity by time, which velocity is a vector 2, you get acceleration. That's exactly what's going on. So let's look at the first of those, speed. As we said, that's the change in position with respect to time. In other words, change of position divided by change of time. In other words, time rate of change in position or distance. Now, there's two types of speed we can talk about. Okay? When I drove from home to work this morning, like I said, let's say I went about 18 miles. Let's say it took me about 20 minutes. Okay? Now, if I rounded that up to 20 miles in 20 minutes, I think y'all know how fast I was going, right? What's that? 60 what? Okay, now does that mean I was traveling 60 miles per hour the entire time?
No.
Like when I backed out of the driveway?
No.
Or when I went to that first turn? I better not have been, okay? And does that mean when I was on the expressway I was going 60 miles an hour? Could have been, but on parts of the expressway I'd have been getting some flack from behind, right? Because others were going to be zooming past me. So that is what we call average speed. That's the most common measurement we make. We measure the total distance divided by the total time. That gives us our average speed. So I would be averaging 60 miles an hour coming to work, but it probably, definitely wasn't traveling at a constant 60 mile an hour rate. In my home neighborhood, very much slower than that. Lots of stop signs, lots of turns, short streets, city streets, very slow. Once I got on the expressway, and I get on the expressway pretty soon, then some places 50, some places 60, some 70. Of course, I don't break that, do I? Okay. Now, there is another speed that we sometimes refer to, and you got this little dial in front of you when you're driving. What do we call that? Speedometer. Okay, what is that measuring? Your average speed?
Current speed.
That is what they call instantaneous speed. Not quite instantaneous, but pretty close to it. What's the difference now? The average speed is the total distance you traveled divided by the total time it took. Your instantaneous speed is when you take that denominator, the time interval, and shrink it until it's approaching zero. That tells you how fast you're traveling at that instant, okay? So your speedometer is a good measure, a reasonable measure of your instantaneous speed. So that's what I was looking at. Now, here's just something, don't try it, folks. Oh, but officer, I was only averaging 60 miles an hour, if I counted the time back home, if that little blue light has pulled you over. Don't think it's going to work, okay? Because he's measuring instantaneous, not average, okay? That little radar gun is better. So here's an equation or formula for speed. Distance, scalar quantity distance divided by time is always a scalar quantity. That gives you speed, scalar quantity. No direction associated with that. Just how fast you're traveling, whether you're backing up, going forward, whatever, that's your distance traveled per time. Okay? Now, they don't have a slide there. Let's see if there is one. Let me just scoot ahead. No, I think we'll still get to it. All right, I don't know what was supposed to have been there, maybe nothing. Here is another example of average speed. This time the car is traveling some distance, and at 1 hour they've moved 50 kilometers. Okay? 2 hours they've moved 100 kilometers total. 3 hours, 150 kilometers. What would you say the average speed was between this point, and that point? 50 kilometers per hour. And what you do, 150 minus this, that's change of this difference in, and I want to introduce to you, maybe I should have done it back on this slide. I want to introduce a concept that I like to use when we talk about, let me get my black pen up here, okay? When we talk about a change of position, change of, often I'll refer to that as a delta. Delta P, this could be delta T. Now that's a Greek symbol delta, looks like a triangle, pretty much what it is. What that stands for is difference. Difference is which operation mathematically? Subtraction, exactly. So this is change of distance over change of time. That's just easier to write this. Delta P, delta T, okay? Difference in position, difference in time. And that's exactly what we're doing on this slide. The difference in position is final position always minus initial position. Change of time, final time minus initial time. 50 kilometers minus 50, 150 kilometers minus 50 is 150 minus 50. 100 kilometers. What's your time difference? 2 hours. 100 divided by 2, sure enough, is 50. But you can see that. That's constant speed. Okay. So calculate the average speed between the trip times of 1 hour and 3 hours. So you do the change of distance over change of time. That's going to be your average speed. Yeah. All right. And this is it Wayne? Okay. Now, did you get a lab? You weren't here last time.
Nick printed me off one to do.
Oh, he did. Okay. All right. You might want to get with them also to fill in the blanks.
All right.
Okay, because they did that. We did it Thursday, and some of them got together and finished it up, or came close to finishing it today. And another piece of new news is that I finally got your PowerPoints out on Blackboard under content. So if you want to see those ahead of time, you can, or afterwards, whatever. Of course, on YouTube, you'll be able to see the PowerPoints and hear me talk about them at the same time. That's the advantage of YouTube. But the ones on under content are out there ahead of time so you can look at them before we talk about them. All right, any questions on average speed? Oh, I think they're going to calculate it for us, just like we did. And here's the formula they have on the top of page, first column on page 28. It's another way of saying what was written in words over here. Speed is equal to distance over time. Average speed, when they say average, quite often they'll put a little line over the symbol, okay? That means average, and that's distance over time. So here's how they say it on this one. Average speed. Now we use the symbol V, little v. Remember earlier we talked about, when we were talking about density, what was capital V? Volume. Little v, I told you, velocity. Or speed. They're using it for speed here, because they mean about the same thing, but this is average speed is distance divided by time. Now, if I were writing that, I would say delta D over delta T, because it's a change of distance over change of time. It's not just distance over time. Like you could be, I could be 18 miles from home, and what time is it? 3 o'clock in the afternoon? Does that mean I'm 6 miles per hour? No. That doesn't make any sense at all. It's always a change of speed, how far you travel in what time. It's always a distance, a difference. Delta, okay. And that would be, well, they left it off. We already calculated 50 kilometers per hour. Now you see how important the units are, right? If you hadn't put the units down and just said 50 what? Furlongs per fortnight? Miles per hour? Inches per foot? I mean, what is it? I mean, inches per second? I mean, you don't know what it is until you put, and unless you put your units down. So they have units, put them down. And if you do the calculations right, the units will be right. Miles per hour, feet per second, meters per second, whatever. Okay? All right, that was speed. Now, what's the difference between speed and velocity? Second? Direction. Very good. Okay? Velocity describes the speed, how fast you're going, with the added piece of information, which direction. Where is it going? Like when I drive home later tonight, I'll be going the same 18 miles, but I'll be going to the northeast rather than the southwest. Otherwise, I'll wind up somewhere I don't know. Okay. So that would be what velocity is. It includes speed, but it also includes a direction that speed does not include. Now, the graphical representation of velocity, which has direction, is that of vectors. I already mentioned it to you. The length of the vector is called the magnitude. That's just another word for length. And the arrowhead on the vector points in the direction you're traveling. Because a vector is what they call a directed line segment. It's some length of thing, that's the magnitude, but with the arrow on one end or the other, and that indicates the direction. Okay. Now, here are some examples of travel. This vehicle here is going 30 kilometers per hour to the east. Okay? This one is going 60 kilometers per hour to the east. Okay? And since they're going in the same direction, the vectors are parallel to each other. But this vector has one magnitude, and this vector has approximately twice that magnitude. Now, most of the time we don't draw them that big, but yeah, you would need to do it to indicate your thing. Now, this vehicle here is going 60 kilometers per hour, the same speed as this one, and notice its vector is the same length, but this one's going to the northwest, that one's going to the east. So the speeds of these would be the same, this one and that one. But the velocity would be quite different. Same speed, different directions, therefore different velocities. This is same direction, but different speeds, so that's a different velocity. So velocities can change for two different ways. By speed, by direction, actually three ways, or both, okay? That would also be involved. And we will be, especially remember that we mentioned circular motion, that's going to introduce another kind of an acceleration, change of velocity, okay? Now let's look at acceleration. Boy, they threw them all up here at once, didn't they? As I said before, what acceleration is? The time rate of change at which motion changes. In other words, which velocity changes. Rate at which motion or velocity changes over time. And when they say that, over time, that means change of velocity over change of time. Delta V over delta T. That's acceleration. Now, three ways that acceleration can change. Punch the accelerator, you're going faster speed, right? So your speed could change. But that's not the only way. Turn the car, your velocity is in this direction, you turn the car, you're in that direction, your velocity changed it. The magnitude didn't change, the speed didn't change, your direction changed. Were you accelerating? Yes, you were. Anytime you change direction, you have to be accelerating. Well, I think I talked about this last time. At Talladega, when they changed directions, what do you notice? High bank there. Why? If you didn't have that, they aren't going to change it. Tires, you see what's happening there, you're accelerating. Your tires are pushing you toward the center. If they didn't do it, like if there was ice on the road and they can't push you, you don't turn, okay? So you have to be accelerating. Not on your accelerator, but with the thing, okay? And then you could have both speed and direction changing. Now, acceleration can also be negative. You sometimes call that deceleration, but in physics we call it a negative acceleration, okay? So therefore, which three devices in the cab of your car, as you're sitting there driving, which three accelerate? Yeah, the accelerated gas pedal, that accelerates because it changes the speed. The steering wheel, because that changes your direction. And the brake pedal changes because that slows you down. Gives you a negative acceleration, but it's still an acceleration. A change of speed is an acceleration. A change of velocity is definitely an acceleration, whether it's speed or direction. Okay? So all three of those devices are accelerators. Okay? So maybe the best name for it is gas pedal then, rather than the other. Does that make sense? All right. So here's illustration of those three. Here the car is changing from 30 miles per hour to 60 miles per hour. Is that car accelerating? Yes, it is, because it's changing its speed. This car is changing from 60 miles an hour to 30 miles an hour. Is it acceleration?
Yes, it is.
Yes.
A negative acceleration, but it is changing its speed, so therefore it is an acceleration, a negative acceleration, because remember, your change, yes, was that just changing? The change is always final minus initial. Here your final was 60, your initial was 30. 60 minus 30 is a positive number, 30, and then you'd have to have how long it took, how many seconds or whatever. 30 miles per hour per second. Over here, what's your final? 30. What's your initial? 60. So what's your change of acceleration? Negative 30 miles per hour. So that's a negative acceleration. You'd have to have a time under that per second or whatever. Okay, how about this one? This car is traveling 30 miles per hour this way, goes through a turn at Talladega, and then goes 30. They don't go 30 miles an hour, though, do they? Okay, 30 miles per hour in that direction. Has that accelerated? You better believe it, because it changed its velocity all around the curve. Did the speed change?
No.
No. Okay. Now, quite often when you go around the curve, your speed does change because you slow down to go around it. But that's not that would be part of an acceleration, but it's mostly the direction change. This one's coming in at 30 miles per hour, but leaving at 60 miles per hour. Did it have a change of velocity?
Yes, it did.
Two ways. One in speed and one in acceleration. In fact, if you're talking about these as velocities, what is your velocity here? Final velocity. 30. Velocity here was here. Because direction is part of it, what would you say that was? A negative 30. So 30 minus a minus is a plus. That would be a 60 mile per hour acceleration. Okay, well, 60 miles per hour is a change of velocity. Over whatever time it took, that would be the acceleration. This one, on the other hand, would be, final is
60.
plus 60, initial was
30.
negative 30,
Negative.
because it's pointing in that direction. Because when you're talking about velocities, and that's what we deal with acceleration, then you have to have direction involved with it. So that would be a change of velocity of 60 minus a minus 30
It's a plus 30.
is a plus, and 60 plus 30 is 90.
90.
That would be your change of speed, not change of speed, change of velocity. Change of speed is just 30. Change of velocity would be 90. And so you would have to include that. There it would be change of 60. Okay. So yeah, lots of weird things to do. We're not going to do too much with the curve. I mean, you have to realize it. Okay. We'll talk about this later in the chapter when we talk about circular motion, because that's what you got. Have any of you ever come in I-20 from the east before it merges with 59, right there, fairly close to the airport? I don't know. I think the reason was,
Poor design.
yeah, very poor design, but you see they had a cemetery right behind that. And I don't know if they couldn't get the land or what, but boy, that is one sharp curve. And if you don't pay attention to that speed limit, it drops to what, 45 or something like that? You're going in, coming in around 70, but you should stop to around 60 when you get in the congested area. But then you have to drop more. Otherwise, you're in the cemetery, maybe in a couple of ways, okay? Over the fence, because you can lose it on that curve, especially if there's any moisture, and certainly if there's any ice. Hey, you better take that one slowly. Like you said, poor design. Okay. Get the yakking too much. Let me make sure I haven't missed anything here. I think I have. Well, yeah, I did. Sorry about that. Example 2.1. We're going to back up a little bit to page 28. I wasn't paying attention here. Let me find a good place to write on. Let's see. This is under speed. This is probably good place as any. Let's write on here. Example 2.1, page 28. The driver of a car moving at 72 kilometers per hour. 72, has that got a 0.0 after? Yes, 0.0 kilometers per hour. What's that a measure of?
The time factor is
Say again?
3.0.
Okay, wait, yeah, just right there. 72 kilometers, 0.0 kilometers per hour. What's that a measure of? Velocity or speed, okay? Since it doesn't have a direction, we'll call it a velocity. In fact, we'll call that an average speed. We'll call that V bar, okay? Okay.
Now the book gives you.
Okay, yeah, we're going to get there. Okay, he drops the road map on the floor. Boy, this is an old problem, isn't it? He didn't have GPS. I know, I mean, you don't see many road maps anymore. Yeah, they have them, but okay. Drops the road map on the floor of his car. It takes him 3.00 seconds to lean down, find it, pick it up, and come back up. Okay? What's that a measure of? That's a delta T, change of time. Okay? Now, how far did he travel during that time? What is that asking for? How far? Huh? It could be miles. Could probably in this case kilometer. Huh? So that's a distance. We're looking for the distance. That's the unknown here. Okay, remember how it said solve these problems? As you read the problem, write down what they tell you. Probably not a bad idea to draw a picture if you wanted to. But let's see, with those three pieces of information, what formula or equation ties those three together? And this distance could be a change of distance. Or you could leave off the deltas. Is there a formula that ties these together?
It ties into the speed.
Yes, and what's that formula?
Distance divided by time.
Okay, V bar is equal to distance divided by time. Right out of the book, right? What are we looking for?
Distance.
The distance. So what could we do to solve that for distance? Now remember, you can either plug and chug or chug and plug, right? Which you want to do? Solve for distance or plug in the numbers and solve the numbers? Okay, solve for distance. What would you do? To isolate the distance, get the distance by itself and get everything else on the other side of the equal sign.
Some time on both sides.
Okay, multiply both sides by time. Okay, usually I write it the other way. Here the times divide away, and you have distance is equal to average speed times time. So all we have to do now is plug it in. The average speed was 72.0 kilometers per hour. Time out, team. Something we should have done at the very beginning. Look at your units. Do they match? No, they don't. So we're going to have to get some conversions in here to either get those hours to seconds or get those seconds to hours. Which way do you reckon would be easier to go? I think hours to seconds. So let's start with this 72 kilometers per hour, and let's multiply this. Remember how I said do a conversion? Put you two blanks down, and you might need more than two, but let's do two at a time. You're trying to get the hours to seconds. Does anyone know that conversion, by the way? You may not, but you do know hours to something else. What? Huh? Minutes. So that's going to be our first conversion. Always put the units in their place. This blank is for numbers. This blank is for units. Put the units in their place. If you're going from hours to minutes, which goes where? One goes on top, one goes on bottom. You tell me. Hour on top, minutes on the bottom. Okay, now match the numbers with the units. I thought you said 1 hour. How many minutes is that? 60 minutes. Now that hasn't done anything. That's not your T here. This is just getting your units work. Okay? Your hours go off, and that gives you kilometers per minute. We don't want it per minute. We want it per second. We might have to do another conversion here. What would you put where? Always put the units in their place. Minutes on top, seconds on the bottom. Now match the numbers to match the units.
1 minute.
1 minute is 60 seconds. Now you get rid of the minutes, and now you have kilometers per second, and then you can multiply that, I don't have room over there, times your 3.00 seconds. That's going to be kilometers per second. That's an awfully big unit for such a short time. So we may want to convert our kilometers to meters. So let's do that conversion. Which unit goes where? Second. Which goes where?
Meters goes on the bottom.
Really? If you put meters down here?
No. Meters on top.
Yeah, meters on top, kilometers on the bottom, so the kilometers will cancel out. Now match units with the numbers with the units.
So
Say again?
1 meter. No, sir. Come on. 10 meters.
Say again? 1,000 meters, 1,000 means kilo, is 1 kilometer. Okay, now your kilometers go out, and your seconds go out, and that's going to leave you meters. So if you got a calculator, what you do is multiply your numerators, divide by your denominators. You can do them in any order you want to, but that would be 72 divided by 60, divided by 60 again, times 3, times 1,000. What does that give you? 60, and the units? Meters. And it's probably 60.0 meters, isn't it?
Yes.
Okay? Now, how far is 60 meters? That's 3 seconds driving along at 72 kilometers per hour. Anyone know about how fast that is? Not far from 60 miles an hour. Okay? Not that fast. Okay? 72 kilometers per hour. Drops it, picks it up in 3 seconds, you know. How far has he traveled? 60 meters. How far is 60 meters? If you're on a football field. About how far?
About 60 yards.
Yeah, a little bit more, about 65 yards, okay? Because a meter is a little longer than a yard, remember? Yard, meter, okay? So it's going to be probably closer. Okay, 65 yards, maybe. 65 yards, that's over half a football field length, folks. That's from the bottom of the end zone to the 50-yard line and then a little bit, okay? That's how far you traveled in 3 seconds. Guess what? Not a good idea to stoop down and pick up your map or anything else. Leave it lay, okay? Especially if it's your phone. Leave that down there. Oh, never mind, we won't get into that. Okay. Does that make sense? All right. And sure enough, they got 60.0 meters. Now, by the way, for those who weren't here before, when you have a decimal with a 0 after it, that means that's a significant digit. 2 zeros, that's 2 significant digits. This means that's not 72 kilometers per hour to the nearest kilometer per hour. That's 72 kilometers per hour to the nearest tenth of a kilometer per hour.
So it's not just a placeholder.
It's not just a placeholder. That's giving you precision there. Now, if it was 720, you wouldn't know if that last 0 was significant or not. If it follows the decimal sign, then that is significant. Okay. Okay. And this is not just 3 seconds. That's 3.00 seconds. So that's not just to the nearest second or the tenth of a second. That's to the nearest hundredth of a second. Are 3 seconds. So your answer, since you have input of 3 significant digits, you need to have 3 significant digits output. Okay? It's the reverse logic of garbage in, garbage out. Good stuff in, good stuff out. 3 digits in, 3 digits out. Okay? So you should do 60.0 meters. And that means not just 60, 60.0 meters is how far you travel, to the nearest tenth of a meter there. All right, let's do 2.2. Can I erase that? Everybody got it? Okay. 6.2. A bicycle has an average speed of 8 kilometers per hour. 8.00 kilometers per hour. What's that a measure of? They said average speed. What symbol do we use for that? That's the V bar. V bar. The bar means average. Okay? How far will it travel? Again, what are we looking for? Distance. That's the unknown here. In 10.0 seconds. What's that a measure of? 10.0 seconds. Again, that's a measure of time. This time, let's plan ahead a little bit. Let's first convert that 8 kilometers per hour to seconds. Or you want to go as far as go meters per second. Yeah, let's go on the meters per second. So what are we going to have to do? That's going to be at least 3 conversions. You want this in meters per second. So what you want to do first, it doesn't really matter. Kilometers? Okay, what do you want to change it to? Meters. So which one do we put where? Really? Meters on top, kilometers on the bottom, so you can cancel those babies out. Okay? Now you have to match the numbers with the units. How many meters is a kilometer? How many kilometers is a meter?
A meter is, you said, 1,000 meters.
1,000 meters is 1 kilometer. Okay, kilometer. So that takes care of your kilometers. Now we got to get from hours to minutes. Hours to minutes. To minutes. And what do we put where? Yeah, hours on top, so it'll cancel out, and minutes on the bottom. And what's the unit numbers that match those units?
1 hour.
1 hour is 60 minutes. Okay? That will get rid of my hours here. We got one more to go to get the seconds, so what do we put? Seconds on top. Minutes on the bottom.
1 second.
One.
No, I'm sorry. 60.
Wait, we did that wrong, didn't we? We got over a minute square. You got me in the wrong place here. Well, you're leading me astray here. Okay? All right, tell me what was supposed to be there. See, units are your friends. They'll help you catch your errors. Okay? What goes where? Minutes on top, right? And seconds on the bottom. Now the units cancel out. And how do you match up minutes and seconds? 1 minute is 60 seconds. Okay? I think we're ready to go here. Multiply the numerators. You only got one. No, you got 2. 8 times 1,000 is 8,000. Divide that by 60 and then divide by 60 again.
60 divided by 60 again.
Right?
That will give you 2.22.
2.22. That's meters per second. Okay? So now we can, okay, let's go back to our original thing. What formula or equation ties those 3 together?
That will be V over distance times time.
Okay?
I mean, V will equal.
Are you saying V or D? I don't hear well.
The average.
Average speed, V bar,
V bar, right?
equal to distance over time. Exactly. Meters per second. Yeah. Okay? Now, what we're solving for? Distance. So what do we need to do?
You get distance out by itself.
And how do we do that?
Do everything by time.
Multiply both sides by time. Okay? These will go out then, and you have distance is equal to average speed times time. Now, we've already got our average speed now in 2.22 meters per second. That's the same as 8 kilometers per hour. Multiply that by your time, which is 10.0 seconds. The seconds go out, and that gives you how much?
Meters, 2.22 times 10,
Right?
something like 22.2.
22.2. Don't forget your units, meters. Okay? So in 10 seconds, that bicycle travels about a quarter of a football field, about 22.2 meters. That'd be close to 25 yards. Make sense? All right. That was example 2.1 and 2.2. 2.3 was over here on, see if I can find it here. Okay, right about here, I think. It was after we started velocity. And acceleration. All right, before we got to uniform acceleration, I think. Okay, so let's do it here. Example 2.3. Now, a bicycle moves from rest. What do we mean by that? What do we mean by rest?
Rest.
If something is at rest, what does that mean? Stationary, very good. In other words, not moving. So what parameter could you say about it is true about it? If something's not moving, okay, my car's not moving out there. If I turned it on, what would the speedometer say? 0! So that's what it means at rest, not moving, okay? At rest, that means, and it's starting that way, right? A bicycle moves from rest, so that means its initial VI, that's initial velocity, is 0 meters per second. Okay? It moves from rest to, that means you got a final velocity, right? And what's the final velocity? 5 meters per second, okay? Meter, I can't write. I'm writing 5 in meters at the same time. Duh. Okay. Didn't do. Okay. What you say? 5 meters per second. That's your final velocity. In 5 seconds. What's that? 5 seconds. That's your time. Okay. Now, what's this initial and final? What does that give you? What does initial and final tell you? Second? Okay, start to finish. That's going to give you a change of velocity. What do I like to call that? Delta V, which is also always V final minus V initial. So what would that be? 5 meters per second minus 0 meters per second. So that's going to be 5 meters per second. So that's your change of speed. It's saying, what is its acceleration? So what is the formula for acceleration?
Acceleration would be
change of velocity over your change of time or your time interval. And that would be, in this case, 5 meter per second divided by 5 seconds. And that would give you 1, what unit? Meter per second per second. Now we shorthand that to say 1 meter per second squared. Exactly. An acceleration is a distance per time, or distance per time squared. So when you're talking about your 0 to 60 in 4.3 seconds, that's 0 to 60 is a change of velocity, and in seconds. So that'd be 0 to 60 miles per hour per second. This is meters per second. That would be miles per hour per second. Still an acceleration. Okay? Is that what they got? Sure enough, they did. They even got the units right. Good for them. Let's do example 2.4. Okay? An automobile uniformly accelerates. So that's a sort of a new word here.
From rest.
Yeah. But it uniformly accelerates. I was going to see where it was that said that, but we'll get to it in a minute.
That'd be 0.
Okay? From rest, and what does that mean?
0.
Zero what?
Mile and M.
M, meter per second.
Meter per second.
And what's that a measure of?
What's the measure of?
Meters per second, that's a measure of? Two words that mean the same, except one's a vector, one's a scalar. Velocity, that's your, but which velocity? That's initial. That's what you started at. From rest, and an automobile uniformly accelerates from rest, so that's going to be its initial velocity, at 5 meters per second squared. What's that a measure of?
Final velocity.
Does that look like a velocity? What does that units tell you? See, units are your friends, folks. Say it again. 5 meters per second squared, sure not at any time my clock can tell. Not a distance. We just had it as our answer before. Miles per hour per second. What do we call that? Meters per second squared. No, velocity is meters per second. Distance is meters. What's your A word? Be nice. Acceleration. This is your acceleration. Okay? Accelerates from rest at 5 meters per second. See there it says accelerates at 5 meters per second squared. They gave it to you. Okay? 4 is 6 seconds. That's your time. Exactly. Okay. What is the final velocity in meters per second?
Okay.
Ooh, how are we going to get that? We're looking for final velocity. That's the unknown here. So what formula or equation do we have that relates acceleration, time, and velocities?
That would be
Can I say that again?
delta. You said delta V.
Delta V, I thought I heard someone say, delta V divided by time. And what would that give you? Acceleration, that's exactly right. What are we looking for here? Not as our final answer, but intermediate, we want to know what that delta V is. Okay? So we're looking for this right now. Later we'll go back and figure out what final velocity is, but now what we're going to do. Multiply both sides by time. You got it. Okay? And this is the times will go out, and you have delta V is equal to A times T. And we can figure out what that is. A is 5 meters per second squared times 6 seconds. Notice here, this second wipes out one of those seconds, because second squared is a second times second, or second over second. Yeah. So anyway, it wipes out one of those, and that gives you what? First multiply your numbers. 30, and what units? Meters per second, exactly. Now, that's your change of velocity. And since your initial velocity is 0, this is also your final velocity, because change of velocity is v final minus v initial. And since the v initial is 0, that makes the change of velocity your final velocity, right? So your final velocity should be 30 meters per second. What did they get? 30 meters per second. Good for them. All right, I think we caught up with our slides, with the problems. Now, before we go any further, in fact, we're a little ahead still, look on page 31 or somewhere thereabouts in your book. There's a little green blurb at the top of the page. Science and Society, Transportation and the Environment. Wow. Pretty important stuff, huh? Well worth a read. And think through these questions, okay? Some pretty interesting concepts in there. Some things we don't do too well, do we? Like mass transit, carpooling, walking, bicycling. We don't do those too well, do we? Okay, I think now we're ready for example 2.5. Well, wait a minute. Somewhere on these pages here, and I haven't found it yet,
I'm sorry, Dr. Fowler, what did you just say?
I'm looking for it. Somewhere here on these pages that we're on, we should run into the concept, and I don't see it, of uniform acceleration. We mentioned it once. Does anyone know what we mean by that? Uniform acceleration. Another word for uniform. And I sure don't see it in my book. I know it's here. I know what it stands for. Say again?
Control?
Okay, yeah, meaning it's the same. Constant acceleration.
Constant, okay.
Okay. Ah, here we go. I see it. It's on page 31, at least one place.
Constant acceleration.
Yeah, if you see that paragraph at the end of the first column on page 31, if you got the new book, and going into that little bit of the paragraph on the second column, it says to find an average velocity during uniform acceleration. That means constant acceleration. The acceleration is not changing. Okay? That's what we're talking about in this slide. Uniform acceleration is constant straight line acceleration. Okay? Okay. Here's an example. What would you say about my acceleration right now?
Constant.
It is constant at what level?
Slow.
Zero.
Because my speed is not changing. So my acceleration is 0. Okay? Now, if now I'm accelerating at a positive amount. Okay? So, I don't know if that was constant acceleration or not, but if the acceleration is increasing the same amount of miles per hour or feet per second every second, that's constant acceleration. Constant straight line acceleration. Now, let me tell you this. You can't maintain this very long, okay? Because you're soon going to be going very, very, very fast. Okay. But when you have this uniform acceleration, which is constant straight line acceleration, the average velocity simply related to initial and final velocities in this case. And I think they give you a formula for it.
Yes, they do.
Here it is. The average velocity. Now remember, we had another expression for average velocity a little bit ago. And that was this one. Average velocity, or average speed, was distance over time. Or change of distance over change of time. Right? Here's another formula for the same thing. If you got uniform acceleration or constant acceleration, then you can also average. What if you had 2 test scores? And I said, what's your average? What would you do? add them together and divide by 2, right? So if you have constant acceleration, uniform acceleration, add your final velocity to your initial velocity and divide by 2. We'll be doing this in the next lap. We're not going to have time for it today, so it'll be on Thursday. We'll first calculate a constant velocity this way, and then we'll use this formula to come up with a final speed. Okay, final speed. Okay? So, that's at the bottom of page 31, that formula there. Now we're ready for example 2.5. Okay, let's see what, let's go back and let's clear this out of the way. Okay. All right. 2.5. And example 2.5. An automobile moving at 25 meters per second. What's that a measure of? Meters per second? Yeah, this is speed, which we're going to call V bar. Okay? An automobile moving at 25 meters per second comes to a stop. No, that's not a V bar. That is a V initial. That is your initial speed. Okay? Because that's what you're traveling initially, and then it comes to a stop. What is that? What is 0?
Meters. No, it's the final.
Final what?
Stop. It's the final.
Final velocity, okay? Your V final is going to be 0. It comes to a stop in 10.0 seconds. What's that a measure of? Time, or your time interval, delta t or t, okay? When the driver slams on the brakes. Now here is the assumption here, folks. When you slam on the brakes, we're exerting a constant force. We haven't even talked about forces yet. Constant force, which we're going to assume is going to give us a uniform acceleration. In other words, it's going to stop us uniformly. It's not going to stop us real quick now and then slow down and stop, or vice versa. It's going to be a uniform deceleration, or negative acceleration. Okay. How far did the car travel while stopping? What are we looking for here? Distance. There's your unknown.
Right. Now.
Okay. How are we going to figure this one?
Well, we got a few things.
We got what?
We need to, we can add them and divide by.
Exactly. If we can get our V bar, we can use time and distance to figure out, what that distance is, okay? So V bar is now, what's that formula we just had? You just said it? V initial plus V final divided by 2. That's the other formula for V bar. And in this case, it's what? 25.0 meters per second plus 0 meters per second divided by 2, and that would be 25.0 meters per second divided by 2 would be 12.5 meters per second, because 2 doesn't have any units there. It's just a divisor, okay? Now we have V bar, we have T, we're looking for D. How do we get that?
Just plug and chug.
Okay, but what do we plug and chug it into? You got to have a formula.
Distance
Okay, distance.
equals V final plus.
Okay, say that again. Distance and what? Help him out. Help him out.
What is it?
What's your formula?
Please help me out.
You got, say again?
It will equal V.
Help me, help me. This is one we had a while back. We didn't forget it, did we?
No.
No. No, we shouldn't do that. We got to use them.
No.
If you think about your units, it's going to help you a lot. How do we measure average velocity? Meters per second, that's distance per time. So average velocity is distance per time. There's your formula. Units are your friends. Now what? What are we looking for?
Distance.
Distance. So how do we get it?
Time.
Multiply both sides by time, and that gives you distance is equal to velocity, average speed times time, and in this case our average speed was 12.5 meters per second times 10 seconds, 10.0 seconds, and that gives you,
25.
so D is equal to, the seconds cancel out, 125 meters. All right. He slams on brake, takes 10 seconds to stop. How far has he traveled? 125 meters. That's from one end zone to the other end zone plus some. Because you see, end zone, goal line to goal line is 100 yards, which is less than 100 meters. Go another 10 yards, that would be 120 yards. It's more than that. You have gone more than an entire football field slamming on brakes at 25 meters per second. It's not that fast, folks. I'm guessing it's about 40 miles an hour, maybe. Wow. That's a lot of distance. That's why we don't tailgate, isn't it? Because if you tailgate too close and they slam on brakes, you slam on brakes, guess what? You're in them. You got that bumper in your face. Okay. We don't want that. Okay, 125 meters. Let's clear that out of the way. And let's do 2.6. Oh, why did I do that?
What erase?
Let's see, I don't think I can go back. So what I have to do, what is the deceleration or the negative acceleration of the automobile in that example? Why wasn't I paying attention? Well, what's our formula for acceleration?
Acceleration, we have change of velocity.
Change of velocity
Over time.
over time. We know our time. That was 10 seconds. Okay? Now, what was our change of velocity?
It was, that's what the stop was.
Yeah.
That was
So it went from 25 meters per second to a stop, which was 0. So the change of velocity was
25 meters.
negative 25.0 meters per second because it slowed down. Okay? So what was its acceleration?
10 is not, okay. So we just do 25
Divided by 10.
10.
Right?
That'll give you 2.5.
2.50. You got 3 significant digits. Meters per second. Squared. Meters per second. Because it's an acceleration. Now,
One cancel out there.
no. You're dividing each of them so they go together. It's actually a negative 2.50 meters per second squared. That's its acceleration. The deceleration, then you can drop the negative sign and make it 2.5. So I think they answered negative 2.50 meters per second squared. All right, good deal. Does this making sense? All right. there is a little concept applied there that really is a pretty interesting thing. It's talking about dripping water from a radiator, but you'd have to know the rate of drip. It says at 1 drip per second. You could make up some stuff, but actually I've heard of a physical science class doing this. We'd have a little bit of problem with it because we really don't have a nice level parking lot. But if you took one person or maybe two sitting in a car with the door open in a flat level parking lot, no other cars around, please, okay? And then in the car you got a guy with some traffic cones, a whole stack of them, okay? And someone else has a stopwatch. Every time a second clicks by, you put out a traffic cone because the door's open, just put it out. Now you have the people at the back of the car pushing on bathroom scales. Now why would you push on bathroom scales? That measures force, which you were going to get to later. And if they're pushing with a constant force, then you can measure how far you travel and how many seconds. You can get your velocity. You can get your acceleration. Boy, you can do lots of things with that. I wish we had the situation we could do it. Probably going to be a little tough, so we probably won't. But you can think about that. That's what that concept applies is talking about. All right, now we're ready for the second part of the chapter, which is forces. Okay? Now, if I say force, what do you think of? Is there any? Yeah. Okay, I see a push going on there. And I can remember, this is the truth. My high school physical science teacher was the head football coach at our school. That head football coach at our school was named Pooley Hubert. Now, most of you are way too young to ever remember him. Pooley Hubert, that was a nickname, okay? He was Pooley Hubert, okay? He was one mean old cuss, okay? I mean, no one wanted to mess with him because he was tough. He played football at Alabama, and he was either on the throwing or receiving end of the longest pass in Rose Bowl history. Okay, I don't know how, 99 yards or something like that. Now, of course, it wasn't a pass that long, but that's how long it went. I don't know if that still stands. It probably does, but I don't know. But that was back when they played the single wing offense, which no one plays anymore. The closest you get to it is the option, but he was one mean fella, okay? He was tough. And but I can remember, and he talked just like Bear Bryant. I don't think he played under Bear Bryant, but he talked just like him. Rah, rah, rah. He said, a force is a push or a pull, And so when you said a push, that was Pooley Hubert right there. A push or a pull, that's a pretty simple definition of what a force is. But let's do a little historical background on it. Way back in Aristotle's time, remember this is a couple hundred years before Christ, so this is way back, BC, okay? Aristotle said that heavier objects fall faster than lighter objects. Now, I did that one in class the other day, right? I did 2 pieces of paper, and if they weighed the same, Aristotle said they should fall at the same rate. But I balled one up that still weighed the same, and it went right faster. So Galileo took care of that. But he said objects fall faster. He said objects moving horizontally require constantly applied force. And they sort of seem like they do, but, we'll get to that too. He also relied only on thinking. He didn't do any experimentation. That came with Galileo and Newton when we got the scientific method. So this is Aristotle. He talked about continually applying a force, so he mentioned forces there. On the other hand, here were Galileo and Newton. By the way, Aristotle would be a good paper topic. Galileo would be a good paper topic. Newton would be a good paper topic. Any of the things we talked about, the people and the theories and other things, they could be paper topics. Hint, hint. Okay. Galileo and Newton said all objects fall at the same rate. Okay? As long as there's no net opposing forces. And actually, we did this before. It was in a physics class. I can't get to it anymore, but in the back of room 259, there is a locked door in the back of that room. And I found someone who had a key to it. They let me in, and it has just a stairwell going nowhere. Okay? So you can go up to the third floor. You're not part of the main third floor, but there is a window there. And I had a 1 gram mass and a 1,000 gram mass. Okay? I was going to drop them out of the third floor window, and the rest of the class were downstairs, well back from the building, and they were going to tell me which one landed first. And which one you reckon landed first?
1,000.
Okay, that's what Aristotle would have said. And guess what Aristotle was? Wrong! No. Okay. Okay. When I dropped them, sure enough, at the bottom, they landed the same thing. Now, actually, they didn't the first time. We didn't realize, I never could have done this again in my life. Someone, for some reason, there was like a fishing line going across somewhere there, and when I dropped them, one of the hooks caught on the fishing line, and it swung around. But except for that, they fell at the same rate. I did it again. They were fine. Galileo and Newton said that. Okay? And indeed it's true. No force is required for uniform horizontal motion as long as there's no resistive force. We're going to get there in a minute. This is what Galileo and Newton came up with. And what they did, they thought, reasoned, but also measured, experimented, and found out. Okay, I see a little bit of antsiness. I bet you we're over halfway through with the class, aren't we? You need a 5-minute break?
Yeah, just kind of.
Okay. Why don't we take a 5-minute break? We'll pause here, and I should have done it when we started forces. I wasn't thinking. Sorry about that. All right. We finished this slide pretty much, so let's move on to this. What is a force? Now, a push or a pull. Very, very good. Capable of changing an object's state of motion. Now, what do we call a state of motion?
Rest.
Okay, yeah, it could be at rest. And what does that define? How would you define rest?
Not moving at all.
Okay, and what parameter would you know a value for there?
0.
What is 0? If it's at rest, second?
Negative.
Velocity.
The velocity is 0 if it's at rest. That means it's not moving. Its position doesn't have to be 0. If that's 0, it could be over here. So it doesn't have to be a 0 position. It has to be at a 0 velocity. Okay? So changing an object's state of motion would mean changing it. Okay? So if it was at rest, you make it move. Or if it was moving, you make it veer or stop or something like that. You change its velocity. Think of state of motion as being velocity. A push or a pull capable of changing an object's state of motion. Now they show here in the text, this to me looks like an ammunition ship, frankly. It's some sort of cargo ship. And it looks like a U.S. naval one, and it wouldn't be ammunition ship because they don't go that high of a number, 146. It's some type of a ship with, maybe it's not U.S. Navy, I don't know. But anyway, it's some sort of cargo ship. Now, notice what's messing around the bow and the stern there. Little tugboats. And that's what they're showing here. What if you had a, medium-sized tugboat over here pushing 1,000 units to the east, okay? the ship's at rest. There's that cargo ship. Let's say it's pushing on its stern. You had two little tugboats pushing on it with 1,000 units east. Those would be forces on the boat that's capable of changing the boat's motion, the ship's motion. That would be a net 2,000 units to the east. Now, what if, strange, one little tugboat was pushing here, say on this quarter to the east, but another tugboat, not knowing that, was pushing up here on the other side of the ship to the west. Is that going to change the motion of the ship? No, it's just going to sit there and get bent or something. No, it's just going to sit there because the net would be zero. So forces, guess what? They have magnitude, they also have direction. So they are what kind of quantities? Magnitude and direction? Vector quantities, exactly. Now, what if you had one little tugboat back here pushing with 1,000 units to the east, had another hog of a tugboat pushing this way with 2,000 units to the west? What's going to happen? Yeah, this tugboat back here is going to have the ship coming up, pushing it backwards because you have a net force 1,000 units to the west. So forces are like velocities and accelerations. They are vector quantities. You have magnitude and you have directions. So 1,000 plus 1,000 could equal 2,000. If they're in opposite direction, it could equal 0. Or 1,000 plus 2,000 could be 3,000 if it's this way, or 1,000 if it's that way. You need to attach a sign or a direction with it so you know. Now, overall effect is determined by the vector sum of the forces. That is, the net force on the object. Now, here's another sort of dumb example of that. When we first moved into the house where we currently live, we loved the place, the lot, because it had a lot of trees. The trouble is it probably had a few too many trees. I guess the previous owners just didn't want to take down any trees. And there were these two really scrawny pine trees that had grown up under the canopy of great big pecan trees and oak trees, and they had grown up all kinds of crooked and mangled with hardly any canopy at all because they couldn't get any sun, and they were trying to get to the sun, but they were underneath these other trees. They were in really pretty bad-looking trees. And we decided we really need to take those down. So I didn't have a chainsaw, but my father-in-law did, so he came down from Huntsville, brought his chainsaw, and he brought a long length of rope, okay? And he also brought down my brother-in-law from Huntsville, and we threw the rope as high up in the tree as we could to get over a limb of a tree, and then we got the two ends of the rope. Now, if we wanted to get the maximum pull so we could guide the tree, we didn't want the tree falling into the house or into any other valuable trees. We wanted it to fall down in this one place. So to get the maximum pull, we'd have taken that rope around the tree way up high there, and Dan and I would have both been pulling, and Mr. Brazil would have been sawing on the tree there, and we could then direct the tree this way. And that would be the greatest net force if we both pulled side by side. Did we choose to do that? Why not? Because then the tree's going to fall right on top of us. So we chose not to get the maximum pull. So I moved over this way away, and Dan moved over that way away. Now we were pulling, but part of our pulls were in this direction, but part of them were in opposite each other. So we were pulling against each other in some respect, but then in the other dimension we were pulling toward each other. That's vector addition. Okay? We chose to go that route, even though it wasn't the maximum net force. It was the safest net force for us to do. And sure enough, the tree fell right in between us. Okay? So those net force. You've seen that all the time too, right? Pay attention to guy wires on telephone lines, power poles. Okay, if you have, and when I drive up to Winston County, we parents-in-law had a lake place up there on Smith Lake, and some of the bends in the road, those old country roads have, and the power pole will be here and then there, and when they change direction like that, this line is pulling this way, that line's pulling that way. If you don't have anything else, that pole is going to bend and ultimately break. So what do? You put guy wires just about even between that bend on the back side, and they're pulling this way, trying to keep that pole upright. Pay attention to those when you're driving down the road and see just about every time you have wires coming off at an angle, you got to have a guy on the back, guy wire, okay, on the back side. Net force. You want the net force there to be 0. Don't want it to be in this direction, otherwise the pole bends or breaks. And you can tell when you don't have enough force on that guy wire, you will see that pole bending, okay? And need to fix it. Okay, now, talking about forces, there are 4, we're not going to talk about all these, but there are fundamental forces, the most basic of all the interactions, okay? Some of these we mess with every day, like gravitational forces. Gravitational forces, and we'll get to this later in the chapter, are mass interactions, okay? The only reason we revolve around the sun is because the sun is one huge, massive, it's not huge for a star, but it is a huge, massive ball of gases, okay? Huge, okay? A lot of mass. The Earth has a fair amount of mass too, and it's the product of those masses determine the force they're pulling. Now, if we weren't going that direction, we'd be heading right toward the sun. But fortunately, we're going in this direction. We'll talk about that later. But that is mass interactions. Same thing with Earth and Moon. The Moon's moving in this direction, but the Earth is keeping it revolving around it, just like the sun keeps us revolving around it. So the motions of the planets, the stars, the galaxies, all these things are mass things. So gravitational forces, believe it or not, are fairly weak forces, but they sure travel a long distance. How far is it between us and the sun? Anyone know? About 93 million miles, and yet it's keeping us in its orbit. Just think how far Pluto is out there. That is way, 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 way further, and it's still going around the sun. Now, the next of these, they're a little bit stronger, but they don't go nearly as far, electromagnetic forces. These are, gravitational forces are mass interactions. Electromagnetic forces are either charge or magnetic interactions. Okay, if it's electric forces, that would be charge interactions. Magnetic forces would be is the pole interactions, the magnetic poles. Okay, now why do we say that's stronger than gravitational? Have you ever seen the experiment that you comb your hair with, if you got some, okay, laugh, okay, with a, I think probably a rubber brush, you know, a hard rubber brush, and then have little scraps of paper and hold that near, and you can pick up the paper with it. Okay, what was going on there? Static electricity, absolutely. When you're brushing your hair, now, this only works if your hair is, you know, relatively clean. If it's been a few days and it's a little on the greasy side, it's not going to work too well. Or if it's very humid that day, it's probably not going to work too well. But if it's a fairly dry day, your hair is fairly clean and you got enough of it, that you do. What you've done with the rubber comb in your hair, you've knocked off electrons off your hair onto the comb. So it winds up being net negative charge. Well, those little pieces of paper are neutral, and they feel that, and they get attracted to it, and it'll pick it up. Well, those little pieces of paper are being pulled down by the Earth's gravitational force, right? That's why they're sitting on the table to begin with. They're not floating around, but you get your electric charge there, electric forces, electromagnetic forces, you can pick them up, overcoming the gravitational force. So actually the electromagnetic force is a stronger force, but it doesn't go nearly as far. The Earth is pulling down on those pieces of paper from a long distance away, but you have to get pretty close to it before you can overcome that. But you can overcome it. So, basically have to do with charge interactions or magnetic field interactions. You're dealing with electricity and magnetism. Hang on, chapter 6, we'll talk about that as far as we go now. You're also dealing with atoms, molecules, and all of chemistry pretty much is dealing with electromagnetic forces. Why is it that two hydrogens connect to one oxygen and make, what does that make?
H2O.
Water, exactly, okay. Why does that happen? Because hydrogen only has one little electron floating around it, so it tends to be a little bit on the positive side, whereas oxygen has lots of electrons, but it has 6 electrons in its outer orbit, okay, and it wants to have 8. Hydrogen would love to have 2, so they share 1, and they share 1. So now oxygen has 8, hydrogen has 2 each, and they're happy, okay? And that's what makes a water molecule, because of that electromagnetic interaction between those, okay? That's why chemistry happens, pretty much, because of sharing of electrons, exchanging of electrons, those electrostatic forces. Now, tell me what you know about a single atom. Pick an element, any element, except hydrogen. Pick an element. Second, carbon, great element. It has 6 protons, 6 neutrons, and 6 electrons. Now, where do the protons live? In the nucleus. And so do the neutrons live in the nucleus. What's true about all the protons? They have a positive charge. So here you have 6 positive charges living in this tiny, tiny, tiny little nucleus. Why aren't they blown apart? Why, electrostatically, they should be repelling each other like crazy. Now, the electrons are floating around here. They're negative charge. And that's what keeps them close to the nucleus, because of that positive here, negative here. So it keeps them floating around. They don't go flying off somewhere most of the time. But why in the world, what holds those 6 protons together in that tiny little nucleus? These are the weak forces. They call them weak, but they're way stronger than electromagnetic forces. Way, way stronger. But guess what? They act for very small distances. Very small. When you're talking about the nucleus of an atom, you're talking smaller than nanometers. That's one, let's see, a millimeter is a thousandth of a meter. A micrometer is a millionth of a meter. A nanometer is a billionth of a meter. So I think you're talking even smaller than that, like a trillionth of a meter. I mean, just really, really small distances. They're very strong forces, but they're weaker, but they don't go very far. They're involved in certain nuclear reactions, holding that nucleus together. And then, well, actually, that's something even in between. I was describing the strong forces there. That's what holds that nucleus together, is a strong force. Outside of that, there's weak forces that are not as strong as strong forces, but much stronger electromagnetic forces. Those are the 4. We're not going to mess with any nuclear reactions, okay? Promise, okay? We won't do it. So we're not going to deal with those. We'll deal with these in this chapter. Gravitational, electromagnetic we'll deal with in chapter 6, okay? But those are the 4 basic forces of nature. Now, these are all the forces that we talk about force at a distance, fields of forces. Now, pushing on a chair, that's not a field force, that's a contact force. I can't make the chair come unless I pull on it or push on it, right? So these, from long, long distances, they happen. So those are the fundamental forces. The others are going to be applied forces. So we're going to talk about 3 ways of forces interacting. We're going to start with the simple horizontal motion on the surface of the earth, say. Okay? It could be in the air somewhere else, but it's a horizontal motion, flat, level motion. Okay? Now, this is what old Aristotle said, that a continuous force is necessary to keep an object moving. He said it was. Galileo and Newton said, no, not really. Okay? Now, here's the difference. Here's what Aristotle was observing. And remember, that's all he did. He made observations, but he didn't test them. He said, if I roll a ball on the floor, it's going to roll for a while, but slowly, slowly, it's going to stop. And in order to keep it rolling, I've got to keep pushing on it. Have y'all ever watched that crazy sport they do in the Winter Olympics? Curling? Okay. Craziest thing I've ever seen. Someone slides a stone over the ice, and you got people in front of the stone sweeping, sweeping, sweeping. I mean, it's the crazy thing to look at. Yes, it's an Olympic sport. Okay. Canadians do real well at it. Okay, never mind. Okay. They have a lot of ice up there. Okay. So basically, their sweeping is to get anything out of the way of that. But then when they want it to stop, they stop sweeping, because then they start hitting resistance. And see, Aristotle had never seen them do that, So it isn't a continuous force that needs to keep an object moving. It's just no resistive force to stop the motion. That's the difference. No, the absence of an unbalanced force, that keeps it moving. A natural motion, that would be it. If there is an unbalanced force, like friction or something else there, then the stone starts slowing down. Okay. Here's sort of what we're talking about. If you're rolling the ball this way, now it doesn't look like it is, but the ball's rolling in this direction. Okay? I don't have a ball in here that I can roll, but if I would, how would you know it's rolling or not? If your eyes were closed. You could hear it. Now how could you hear that? Because you've got something bumping into something else and sending out a little sound wave. That vibration that reaches your ear means there's some sort of reaction. So if you can hear that moving across the floor, just like you can hear that. I didn't think of that. I can roll the chair, but you can hear it rolling, and sure enough, it stopped. Because that noise meant there's some resistance there, and that resistance is what's making the noise. Now, if we had waxed perfectly this floor, and all of the greased perfectly all of the bearings in those wheels, and everything was as slick as it could be, I could probably roll that and you'd hardly hear anything, because everything was frictionless. So the friction is indicated by the noise you hear. That means there was a resistive force. Okay? So it's rolling in this direction. But guess what? Even if we had absolutely no friction on the floor, so there was no force from the floor to the chair, you still have a little bit of air resistance. Okay? Now remember the pieces of paper? One balled up and one flat. And the one that balled up hit the ground first because of air resistance on the surface of the other one. So same thing would happen if I had a hammer in this hand and a feather in this hand, right? What do you think would happen if I released them at the same time? Hammers, and that's why Aristotle said heavier objects fall faster. But you know what they did on one of the trips to the moon? They carried a hammer and they carried a feather. And one of those astronauts released them at the same time, and guess what? They hit the surface at exactly the same time. Why?
Very low gravity.
There's no gravity had nothing. It still went down. That means there was gravity. Sure, it's less gravity than here, but not enough to keep the hammer from falling. What happened? There was no air resistance, so they did fall at the same rate. So sure enough, in the absence of unbalanced retarding forces, things fall. Now that was vertical motion. We're talking horizontal. If this were on the surface of the moon and you had a perfectly slick thing, you rolled the ball, it's going to just keep on rolling because there would be no air resistance. And if you had a perfectly slick floor, there would be no friction on the floor either. So the net force on this, once it leaves my hand, I'm exerting no more force on it, right? So there's no more force in this direction. All the forces are in the opposite direction. I should be doing them this way, okay? All the forces are air resistance and frictional forces are pushing against it. So it does slow down and ultimately stop. The net force is against the motion. Now, if I was able to apply a force, and I know it happens in cartoons all the time when you hit the golf shot and it doesn't quite get to the hole, you go, okay, trying to blow that ball on into the hole. Then you're applying a force to it this way to overcome these forces, and in that case, the net force would be 0. Now, does the net force of 0 mean you have no motion?
No.
Why not? It means, say again?
You have other forces first of all.
No, net force being 0, meaning no other forces. That means you have no change of velocity. So if you had an initial velocity and no net forces, it's going to maintain that initial velocity. It has no acceleration. That's the key. And we're going to get into that a little bit later. So, now let's look at the concept of inertia. What does that mean to you, inertia? Say again? What's the first 5 letters there? Yeah. Inert. What does that mean? Inert. Nothing happening, right? Inert. Nothing going on. And that's sort of what people think of inertia. I can't mow the yard. I just can't overcome my inertia. What's that? Ah, very good. Excellent, excellent, excellent. That's what inertia is. It's the measure of an object's tendency to resist changes in its motion, including at rest. So if it's initially at rest, it wants to stay at rest. But if it's initially moving, it wants to keep moving unless there's unbalanced forces there. That's what inertia is. The measure of an object's tendency to resist changes in its motion. Okay, so let's see. Since you answered that question so correctly, I know you, Tristan, right? All right, so what I'm going to do is throw you a ping pong ball. Any problem with that? Well, yeah, but if I had one. Okay? Any problem? Okay, if I throw it hard enough,
It probably hit me.
it might. And would it hurt? Not particularly. Okay, now, bowling ball. Whoa. Now, what's the difference there?
Weight and mass.
Okay, specifically mass. Inertia is related to how much mass there is. A bowling ball has a lot more inertia than a ping pong ball. You know what? I can kick a ping pong ball just about any time I want to, and I'm not going to mind too much. But I don't go around kicking bowling balls anytime I want to, unless I'm sure I've got on my steel-toe shoes and, it's still probably going to hurt a little bit. Okay? So, inertia relates to mass. You said weight, but really mass is a better word there. Okay? Now, where is it that we would probably have no external forces?
Space.
Yeah, the final frontier. No, okay. Space. Now you have to get way away from any planet, any star, any moon, any asteroid or anything else. But if you get far enough away, certainly there's no air resistance up there. So natural motion in free space is constant velocity. No change of motion. So guess what? Aristotle, wrong. Okay? It's not going to tend to slow down. It's going to tend to stay at a constant velocity if there's no external forces. Now, Aristotle did try to account for this to give him credit. He said there's one set of rules for terrestrial motion, that means on the surface of the earth, and another set of rules for celestial motion, which is out there in the sphere somewhere, you know. So he tried to overcome that. Huh? Did someone say
I
something?
said, yeah, he tried everything, huh?
He did. He tried to cover all the bases, or acids, or wherever. Never mind. Okay. So, when you have no unbalanced forces, motion continues unchanged if you have no unbalanced forces. Okay? Now, if you have what they call a retarding force, like air resistance or something like that, or friction, that tends to decrease the speed. No matter where the motion is, it decreases speed. Now, if you have a boost, like you give some sort of a force from behind, like a rocket, you know, a retro rocket or something like that, that tends to increase the speed. Boost increases speed. If, however, you're going along like this and you have a sideways force, that usually doesn't change your speed that much, but what does it change?
Direction.
Your direction, and that is a change of velocity. So you are still changing the motion. Because constant motion means straight line motion, level motion. Okay. Now, here's the result. A retarding force would be if you fired a retro rocket. Here's this rocket moving along at a constant speed, or a spacecraft moving along at a constant speed. You want to slow it down. You fire a rocket that way, you know, so the exhaust goes that way, so it slows it down. That's a retarding force. It slows down the speed. Okay?
Parachute.
What's that?
Parachute.
Yeah, well, that wouldn't work in space.
No,
Fine.
no.
Yeah, okay. So, how many parachute clubs are on the moon? Yeah, no, don't even try. Okay. Yeah, it wouldn't work too well. However, if your rocket was sending an exhaust in the other direction, that's going to increase the speed. Okay? But if you had some sort of force acting perpendicular, like a rocket or something else, that changes the direction. May not change the speed much, or any, but it would change the direction, which is a change of velocity, and a change of velocity is an acceleration, and we're going to get to this in a minute. Accelerations equate or relate to forces, big time. All right, that was horizontal motion. I hate to take up class time for this, but it may be worth it. Let's say you're in an aircraft flying at 500 miles per hour, constant altitude, 500 miles per hour. What's the net force on that airplane? Is there any?
What's the name?
Net force on the airplane.
Yeah, because you're,
Say again?
should be yes, because you're at constant velocity.
Yeah, okay, it's a constant velocity.
Yeah, you have a net force to keep pushing on to keep you at that velocity because there is drag on you.
No.
There is friction.
No, it's
Okay. The net force on that aircraft would be zero if it's constant. Even if it's going 500 miles an hour, the net force is zero. You're absolutely right. There are forces on the plane, but big times. Gravity's pulling down on that plane like crazy. But then lift, remember Bernoulli's force, is pulling up on the plane. But if it's flying level, those two are equal and opposite. And sure, you have a lot, if you're going 500 miles per hour, you have a lot of wind resistance, a whole lot of wind resistance. But you're also firing your jets on that way, and that's pushing, and if you're going at a constant speed, your net force is zero. Sure, there are forces acting on it, big forces acting on it, but your net force is zero anytime you're in level flight, constant velocity. Now, if you're speeding up, the net force is not. If you're slowing down, the net force isn't. If you're elevating the net force, all those have net forces, but horizontal flight, constant speed, even at 1,000 miles an hour, constant speed, the net force is zero, but the individual forces are big. Okay, for sure. Okay, let's talk about falling objects. Okay, and part of the reason when we're talking about horizontal, let's go back to this. Not those, but this one. The ball on the table, you might say, yeah, there's forces acting on it. The floor, the friction of the floor, the air resistance, applied forces. But guess what? You've only hit some of the forces. Gravity is still pulling down on that ball. But the table or the floor is pushing up on the ball. So those net forces are zero. Just like these net forces zero down here. Not up there, that's why the ball slows down. That's why the chair slows down, because the net force is in this direction. Okay? Now, when we're talking about vertical motion, you don't have a force pushing up on it. All you have is gravity pulling down. Well, I say you don't have a force pushing up. As long as the velocity of the ball is pretty slow, you don't have much force pushing up. Okay? Now, by the way, let me make sure I haven't skipped something. No exercises here. Oh, here's a thing. This book has these things called myths, mistakes, and misunderstandings. This is sort of a dumb one to put here, but I have heard people play around with this. Do you get wetter if you walk in the rain or run in the rain? Okay? Why?
I think running because you're like catching the drop.
Okay.
You're like
This is why this comes from.
How fast you run.
Okay.
You're like getting more
You're
drops
skinny
per
like
the
drop.
space.
You're covering the larger surface.
Okay, this is exactly why this is an interesting question. Because, you come up with all these things. But really, what determines how wet you get is how long you're in the rain. So, if you're running and you get out of the rain sooner, then you're less wet. But if you're running 10 seconds or walking 10 seconds and the rain's constant, you're just as wet. Now, distribution of the rain, you'll get more rain wetter on the front side and less on the back side. Yeah, and you feel like you're wetter, but you're still just as wet overall. It all depends on how long you're in the rain. So that's what their little mistakes and misunderstanding. What does that have to do with forces? I don't know, but they put it in here. But anyway, you can read them if you'd like. Okay? So falling objects. Here we have always, just about always, a net force. And what's that force? Gravity is always pulling that ball downward. Or that, arrow, or that bullet, or that anything, it's always pulling it downward. So you don't have the tabletop pushing up to replace to equalize the gravity pulling down that you did with horizontal motion. Or with the plane, the gravity pulling down, but the lift, Bernoulli's force pulling up. Okay, you don't have that here. You have just a net force down. So if you have a net force downward, this thing is going, I keep saying this, the book hasn't gotten there yet, it's going to accelerate. They haven't given us that, but that is indeed true. And what does acceleration mean? How do we define acceleration?
Change of velocity.
Change of velocity for change of time. Is velocity increasing on this ball from here to there? Sure it is. Up here it was at rest. Yes, you released it from rest, and then it's going very slowly here because this isn't 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 balls there. That's one ball, but it's a slow release. It's what it is, it's a camera in a perfectly dark room. The camera, the aperture is always open. But what you have is a strobe light. Okay? Very regular strobe light. I think it's like 1/100th of a second. It flashes. Okay? So it's a strobe light. Your camera is always open, so the first time it flashes, it catches this. The next time it catches the ball there and there and there. It's the same ball going downward, but it's the same time interval here. And what do you notice? The displacement of the ball is very small here, a little bit bigger here, a little bit bigger there. So it's accelerating downward because there's a net force downward. That's what causes the acceleration. I'm jumping ahead. But you can see the velocity is increasing. It has a positive acceleration downward. That's what the difference in the falling object. Now, how far does it fall? Whoa, I thought we had a thing there. We don't. I guess we'll get to it later. We call this free fall. Now, what that free fall means, falling under the influence of gravity without air resistance. Now, do you think that pool ball there had no air resistance? Yeah, if there's any air in the room, it's got some, okay? But the speeds here are so small, the air resistance is sort of negligible, okay? I can remember when I was a kid, we didn't have air conditioning in the car, and in summertime, always the windows were down, and I liked to stick my hand out. I mean, it was fun to do, you know. If I get your hand in the window, you know, but if I could sneak it out there, I would. Now, if we were at stop, I could do that with no problem at all, right? But if we're going really slowly, I could stick it out, but I'd feel some force on me backward. If I stuck it out there, we're going 70 miles an hour, pull my shoulder out, you know, so that's why he didn't want me doing it. He didn't want me to take me to the hospital, okay? So, it all depends on the velocity of the air, okay, of the ball through the air, or the arm through the, you know, that's what makes a difference. So as long as this is small velocities, and sure, it's really small up here, but even down here, that's pretty small velocities. So there's not much air resistance. We call it negligible air resistance. So we call it free fall without air resistance, meaning without much air resistance, okay? And when you're in free fall like that, your distance is proportional to the time that it's fallen, not just the time squared, okay? So this is a proportional to, remember what that meant? That meant D, remember that symbol we had? D is proportional to time squared. Remember that strange symbol? That's a really ugly one there. Proportional to. Now, if we have that constant of proportionality, constant proportionality, you can make that an equation. Let's say D is equal to, what letter would you like to use? Say again? V? Okay, I don't like V because we usually let that mean velocity, so let's pick something else.
D is equal to A.
Oh, he's using an A, T squared. I like that letter a lot better, and guess why? Okay? What would be a typical unit for distance? Say again? I couldn't hear.
He said area.
Distance would be measured in feet, miles, meters, centimeters, inches, furlong, something like that. Okay? What you want to go with? Feet, okay? Feet. Okay? Time would be measured in what? Seconds.
Okay.
And if you square it, you get second squared.
Second squared.
This is feet, and this is second squared. This had better be what unit? Well, that would be equal It has to have feet to match this, but it has to have per second squared to cancel that. And what is a foot per second squared? Hey, what's a foot per second squared? What does that measure?
A foot per second squared is.
What's the unit that for? Feet per square, feet per second squared? Miles per hour per second? That's then,
Feet per inches.
what's that measuring?
Yards, feet, inches.
What does a foot per second measure? What kind of a quantity? Speed or velocity. What's a foot per second square measure? Foot per second per second. Change of velocity, foot per second, acceleration. So that's why we use an A there. That stands for acceleration. That's your constant proportionality. This says the distance is proportional to the time squared. That's what that says. When you put the constant proportionality, that is your acceleration. That's exactly what it is. Now, what we say here, speed, not distance, but speed, increases linearly with time. Okay? So what's our symbol for speed? Speed, what symbol for it? V is proportional to time. Okay? Proportional to. Okay? And guess what? Again, you put that same A in there. V is equal to AT. Now let's see if that makes sense. Excuse me. Okay? What are the units for A? Pick them. You name whatever you want. Feet? No, that wouldn't be it. Feet would be a distance. It wouldn't be an acceleration. It would be a typical units for acceleration. Feet per second? That's speed. Yes, okay, speed per second, or feet per second squared. Times, what's this? Time, what's it measured in?
Minutes,
Or
hours, seconds.
Seconds. So feet per second squared times second, you lose one of the seconds,
Right.
and that gives you feet per second. That's what we measure velocity in. Units are your friends. They help you see if you got it, your formulas right. So speed increases linear with time with the same constant proportionality. Okay? Now, here's the thing that's sort of unusual about this. I sort of suggested to you that the ball was being held here and then it was released. And this was the picture that was taken. But what if you were down here and you threw the ball straight up? How would that picture look?
Just the opposite.
Just like it.
Yeah.
Because you threw it up, not your food, but with a initial velocity of, say, make up a velocity. Give me a number with some units. Give me a velocity. How fast can you throw a ball? Make up a number. 90 miles an hour. Okay. His nose is growing. No, never mind. I didn't say that. Okay. Okay. Let's say 90 feet per second. I don't think he can do it, but let's say 90 feet per second. Okay? If he throws it up there with an initial velocity of 90 feet per second, as soon as it leaves his hand, the instant it leaves his hand, it's moving up at 90 feet per second. How about 1 second later? Is it going as fast, faster, or slower?
Slower.
Slower. And then the next second?
Slower.
Slower. And the next second? Slower. And the next second?
Slower.
So this could be the picture of you throwing the ball upward just as well as going downward. That's what they were meaning with trajectories exhibit up and down symmetry. Now this is a scary thought, but it's so true. I hope this happens more in third world countries than it happens here. The people out celebrating like crazy and fire a gun into the air.
Come on. Bullets gotta come down.
You're absolutely right. With what speed? Say again?
The same, at the rate of the same speed it went up.
Okay. It's going to be close to it. You're right, it won't be exactly the same. But you see, if you fire that bullet straight up, then let's say it's going 900 feet per second. I'm just making up a number. So the first second it's going to slow a little bit. Second a little bit more. Second, yeah. Next second, yeah, and on and on. And at some point, it will reach a stop. And it will stop instantaneously. And then by the same amount, gravity is slowing it down going up and coming down from however high that is. It's going to increase it that same amount that it decreased going up. So by the time it gets back here, it's almost at muzzle velocity. So if you did fire it exactly straight up, it's just like doing that, almost. Now the only difference is air resistance. That slows it down because it's going really fast. So it does. But you see, bullets have rifling, which give it that twist, and that minimizes the air resistance. It still has some, but it minimizes it because it's spiraling through the air. Now, if it's tumbling, that's even worse. Okay, I'm going to slow it down even more. But they exhibit up and down symmetries. So guess what? Firing it randomly up in the air, not at straight up. Yeah, it's not going to hit you, but whose kid is it going to hit over there? And it will be almost as deadly as if you shot them right in the face. Yeah, I know. Scary, isn't it?
It is.
So don't be out there firing randomly in the air because somewhere that bullet's going to land with almost the same velocity you had to begin with because it's trajectory up and down symmetries. Accelerations are the same for all objects. Doesn't matter how big, how small, how heavy, how light, the acceleration is due to gravity. That's all the force on it. Once it's left that, the firing chamber, once it's left your hand when you threw it, after that, the only force acting on it is gravity, except for some air resistance. And the gravity's always pulling it downward. Slowing it down on its way up, speeding it up on its way down. Okay. Second?
It's almost 7:15.
Oh, is it? Okay. This may be a good place to stop. This is the formula we were just talking about. I want to say this one thing about this. This is an idealized formula. Why will that not? Okay, it's just really slow. What, did you have a question? For some reason, this is not responding.
No, let's just do the chase.
Okay. Well, I can't. What I was going to say, if I could get this to erase. There we go. Okay. This is an idealized formula. What this is saying, you have no initial displacement and you have no initial velocity. So this would be the ball being released from rest. If that's zero up there, that's what it is. If you're throwing the ball upward, you would have an initial velocity upward because this is downward, so your distance would vary. So this would be if there's none. The better formula would be this one. D is equal to D other than 0 plus V0t. That's if you started with an initial velocity not 0. This one has an initial velocity 0. Then plus 1/2 AT squared. So if you had an initial velocity, you have to have this term in there. If you have initial displacement, you have that term. But if your initial displacement, initial velocity is 0, then that's your formula. I just want to throw that out. We will stop there, if I can find where we are. Okay, there we are. The next slide is, oops, there it is this one right here. So we will start there next time. Good deal. I'm going to end the recording.